Okay. Okay. Hi, everyone. Okay. Yeah, just in the last little bit, I just want to talk about. Kind of definition of like some cardinal arithmetic, right? So, first, okay, so, okay, so we're going to assume that for each possible cardinality X, you kind of have a representative kappa and such that if the cardinality of kappa equals the cardinality of X, I'm not explaining this right. Okay, let me start over. Okay, here we have the sets of size 0. Well, that's just the empty set. We have the cardinality of the empty set is 0. We have the cardinality of a singleton. Well, a singleton has one element and its cardinality is 1. The cardinality of a set with n elements it has cardinality n, and so on. And then what we want to choose a representative kappa for each possible cardinality. Okay. Oh, sorry. Okay. So just like like the empty set has 0 elements, we say it has cardinality 0. A singleton has 1 element, so we say it has cardinality 1, and so on. And now I just want to like give a symbol for every possible cardinality, not only the finite ones. Okay, actually that we can do this is not automatic, but for now we're just going to kind of brush it, sweep it under the rug. Okay, so for example, okay, so we just choose a symbol for every possible cardinality, basically, is what we're saying. Okay, so then if we have that the cardinality of X is kappa, and F from X to Y is 1 to 1 and onto, then also the cardinality of Y must also be kappa. Okay. So basically, we're choosing a representative of the sets of each like possible cardinality. Okay, and then you have a definition. We define left not. Will have trouble writing this, but to be the size of the natural numbers, the cardinality of the natural numbers. We say like left not. Okay. Okay. So we just give, like, we just call that cardinality of the natural numbers. We give it some fancy name. Well, at least one other thing. We define the cardinality of the real numbers to be C. C for a continuum. Now, what we showed is that our, like Cantor's diagonal argument says that. So a left not is less than C. Is due to Cantor. Okay. Okay, so now we also want to define like the sum of two cardinal numbers. Okay, well, it should be like the cardinality of the union of A and B, where A intersect B is disjoint, and cardinality of A is kappa, and cardinality of B is lambda. Okay, and this gives us a way to define the sum of two cardinal numbers. Well, because if the cardinality of kappa is, if cardinality of A is kappa, cardinality of B is lambda, we just put them together and take that cardinality. And we define that to be the cardinality of kappa, we define that to be the number, or the cardinal number, kappa plus lambda. Okay. And then we have a like little lemma, which I won't prove, which says kappa plus lambda is well defined. In other words, if you choose two representatives for kappa and two representatives for lambda, and the cardinality of A union B is equal to the cardinality of A prime union B prime. And A intersect B is the empty set. A prime intersect B prime is the empty set. Okay. So however you define the like sum of two cardinals, you get the same cardinality of the result. Okay, we can also define multiplication of cardinals. Kappa times lambda, that's just the cardinality of A cross B, where A, cardinality of A is kappa, cardinality of B is lambda. And then we also have another definition. Kappa to the lambda, so that's just the cardinality of the functions from B to A. And here, let me remind you that A to the B is the set of all functions F from B to A. Okay. And then we can prove like all kinds of inequalities and results about cardinal numbers. I just want to do like kind of two simple ones today and then maybe wrap things up on Wednesday. Okay. So one simple thing we can do, you can say that kappa plus kappa is equal to 2 times kappa. Okay. So let's see what let's first like unravel what this means. So, right, kappa to be the cardinality of A. Now we can't just do kappa plus kappa. We want to do like cardinality of A union A, except A and A are not disjoint, so that doesn't work. But we just have to find like a copy of A, which is has the same cardinality of A. Okay, so we define A1 to be let's say 0 cross A, or let's call this A0, and define A1 to be the singleton 1 cross A. Now, cardinality of A0 is equal to the cardinality of A. Cardinality of A1 is equal to the cardinality of A. Right? Because my function, my one-to-one and onto function from A0 to A is just the function that takes 0, comma A equals A for all 0A and 0 cross A. And similarly, so that gives me a one-to-one and onto function from A0 to A, showing that they have the same cardinality. So now, so similarly, A1 and A have the same cardinality. Not only that, but so now we can, we notice that A0 intersect A1 is the empty set. Why is that? Well, all the things in A0 have first coordinate 0, all the things in A1 have first coordinate 1, so none of them can match up. Okay, so therefore, the definition of kappa plus kappa, we can define it to be the size of A0 plus the size of A1. Or sorry, we can define it, we can define it to be the size of A0 union A1, since A0 and A1 are disjoint, and they have both have the same size as A. In other words, they both have cardinality kappa. Okay. But now A0 union A1, that's just the set 0, 1 cross A. This is the cardinal number. This is a natural number 2. Okay, so this is a finite set with size 2. So the definition of this is a Cartesian product 2 times size of A. In other words, this is just a definition of 2 times kappa. Because we use the fact that since 0, 1 has cardinality 2, that's essentially what we're using here. Okay, and to multiply 2 cardinal numbers, we just take the Cartesian product. Okay, so that shows that kappa plus kappa is 2 times kappa. Okay. There are many other things that we can write down, but the last one I want to mention is that a left knot plus a left knot equals a left knot. Sorry, I don't really know a good way to write an aleph by hand, so it just looks like an N. Sorry about that. Okay. So proof. This is basically similar to oh yeah, maybe I'll write down one more to aleph naught times aleph naught also equals aleph naught. Okay, so the proof for this one is basically the same as the proof that the integers have the same cardinality as the natural numbers. Okay, so let's do a proof of this. Okay. Let's construct f from n cross n to n such that f is 1 to 1. If we do that, that will show that the cardinality of n times n is less than or equal to the cardinality of n. And it's clear that the cardinality of n is less than or equal to this cardinality. So we'll be done. Okay, and probably we should do some trick. And I think there's just many tricks, but one trick is you can define f of mn to just be 2 to the m times 3 to the n. Okay. And this gives you a 1-to-1 function from this to this. So f is 1 to 1. And that proves that cardinality of n times n is less than or equal to the cardinality of n. And it's clear that this is less than or equal to this. So by Cantor-Schroeder-Bernstein theorem, they both have the same cardinality. Okay. Now, the set of all rational numbers which are positive actually has the same cardinality as the order pairs of natural numbers. Or actually, what we should do is to say that the set of all rational numbers has the same cardinality as z cross z. Actually, I guess we should say it's like less than or equal to. But Z cross Z, that has the same cardinality as N cross N. Since Z and N has the same cardinality, that's the same cardinality as N. But N, yeah, we have like this sequence of inequalities. And then the Cantor-Schroeder-Bernstein theorem tells us that Q and N have to have the same cardinality because N has cardinality less than Q, which has cardinality less than N. Okay. So yeah, all of these sets are countable, natural numbers, integers, the rationals, and many other things. And then we saw how the real numbers are not countable. On Wednesday, we'll just talk about some of the simple kind of cardinal arithmetic laws you can prove. They're similar to like, the laws are kind of similar to regular arithmetic in some way. But as you can see, like this kind of shows how they're not similar. Like for example, aleph naught squared equals aleph naught, and things like that happen, okay, which is not true. Like 2 times 2 is not equal to 2, for example. So funny things happen when you look at infinite sets is what we can see. Okay. Sorry, I wanted to let you know that I got one response on the questionnaire, which I sent out last Wednesday. And I wanted to point out that one of the comments was that I reached the bottom of the sheet of paper and then moved to the next page too quickly. So I even did that after I read this answer to the questionnaire, and I will just try better not to do that. And so if you see me moving the page too fast, you can like unmute and, you know, say don't go so fast. Okay, or ask me to turn back. And I will try not to do that so that you don't need to tell me, but anyways. Yeah, so there are other helpful things on the that the person who answered responded, but I'll try to fix that one at least. Okay. Anyways, that's it. So I'll see you guys on Wednesday. We'll finish up cardinality. Okay. You know, have a good week. Okay, bye.